Let's just picture this scenario for a second. You walk right into your computer science exam, you flip the page, and boom, you see a totally standard question asking for a flowchart. You need to input 10 numbers and output the total, right? The clock's ticking, so you quickly sketch out a loop, you map out the input for the number, you add it to the total, set it to cycle 10 times, and print the result. Done. You confidently flip to the next page, absolutely certain you just nailed it. But when results day actually arrives, you look at your paper and see a zero. A painful, complete zero for that entire logic sequence. Now, you might be wondering why. Well, it's because under that intense exam pressure, you fell headfirst into a classic trap. A trap that examiners set specifically to catch rushed thinking. So in this explainer, we're going to legally secure every single mark on these algorithm questions by learning to see this logic exactly the way a Cambridge examiner does.
So why does this specific loop score 0 marks? I mean, it seems perfectly logical at first glance, doesn't it? It asks for a number, it loops, and it finishes. But here is the painful trap. It is completely missing variable initialization. Literally, imagine dropping below a critical grade boundary just because you forgot to tell the computer where to start. In real-world computing, if a machine pulls some random leftover number from its memory simply because you didn't force it to start at 0, well, your entire calculation is immediately corrupt. The examiner looks at your answer, sees no initialization, assumes you've made a fatal logic error, and instantly stops awarding marks for any of the subsequent loop logic. No way around it. It's a super strict standard for sure, but understanding it, that is exactly how you beat the game.
Okay, let's dive into this and actually fix that error by mastering the core concept the examiner is hunting for here, which is iteration. An iteration or a loop is really just a sequence of instructions continually repeated until a specific condition is met. So why do programmers rely so heavily on loops? Well, imagine having to write out the exact same input and add instructions 10 separate times, or gosh, 100 times for a larger data set. It'd be highly inefficient and massively prone to human error. Iteration saves huge amounts of code space and keeps programs running beautifully. But to grab those exam marks, you have to prove to the examiner that you know how to control that repetition safely, accurately, and predictably. Let's break down the exact step-by-step sequential mechanism you need to execute to steal those marks. Step 1. Initialize your total to 0 and your count to 1. Seriously, do not skip this. Step 2. Input the number from the user. Step 3. Add that number to your total, and then, this is absolutely crucial, increment your count by 1 so the computer actually knows a cycle just happened. If you forget to increment that count, your algorithm is trapped in an infinite loop forever, and your program crashes. Nobody wants that. Step 4, loop back up, but only until your condition is met. And finally, step 5, output the total, ensuring this happens entirely outside of the loop. If you accidentally output inside the loop, you're going to print the running total every single time it cycles, which frankly is another classic way to hemorrhage marks. Now let's talk about the number 10 for a second. In this specific scenario, this isn't just some random digit, okay? This is your boundary condition constraint. It acts as the absolute limit before the algorithm triggers the final output and moves on. Think about it. If your logic says loop until count is greater than 10, and your count started at 0, you might accidentally loop 11 times. This is known as the classic off by 1 error, and trust me, examiners are specifically hunting for it. They are fiercely scrutinizing your boundary condition to make absolutely sure you understand exactly when that loop terminates. Getting the boundary wrong is basically like building this perfect, impenetrable vault, but leaving the front door wide open. Okay, so we've built the loop, but proving it actually works to an examiner? That requires an entirely different tool. There's a specific framework that makes the difference between a generic, okay answer and an elite top band score. And it is absolutely essential we uncover it before we look at any more code. In a moment, I'm going to show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue super obvious. Grasping this is basically the ultimate mark scheme vault combination. It completely separates the students who are just kind of guessing at algorithms from those who can mathematically prove their logic is solid. And this brilliantly illustrates the trace table. A trace table is exactly how you confidently prove your loop variables update flawlessly during normal data entry. Notice how the numbers shift sequentially here. On iteration 1, the counter is 1, you input the number 5, and the current total becomes 5. Then, as we move right into iteration 2, the counter increments to 2, you input a 10, and boom, the total dynamically updates to 15. It's like a giant puzzle, and the trace table meticulously tracks the state of the machine at every single step. Examiners absolutely love trace tables because they expose invisible logic errors immediately. If your total isn't accumulating correctly row by row, well, your flowchart is fundamentally broken, and this table proves it instantly. Let's escalate the difficulty a bit and see how this builds into even higher level exam territory. Because honestly, just drawing a simple loop isn't going to cut it for the hardest questions on the paper. Top tier answers require trace table reasoning against different types of test data. You need to know how to test with normal data, the everyday numbers the program expects to handle easily. Then there's abnormal data, like if someone types a letter when the program is specifically asking for a number. That should trigger an error. Boundary data tests the exact edge cases, checking what happens on that crucial 10th and 11th iteration. Extreme data involves numbers way outside the realistic scope, like -1,000,000, just to see if the system breaks. And beyond all that, you absolutely must master the difference between validation, which checks if data is reasonable, and verification, which checks if data was accurately copied through double entry. Mixing those two up, that loses you the mark instantly.
Let's actually contrast a flawed answer with a perfect one to really cement this whole concept. A generic student answer might just broadly state, loop 10 times and add numbers. I mean, it shows basic intent, sure, and maybe an understanding of the end goal, but technically, it earns virtually nothing. Compare that to the examiner's safe top band response. Initialize total to 0, use a for loop 1 to 10, input number, calculate total equals total plus number, and finally, output total. See the difference? The perfect response uses the correct technical syntax, clearly defines those starting variables, sets the exact iteration boundary, and mathematically demonstrates the accumulation process. That right there is how you upgrade your thinking to match the mark scheme perfectly.
But here's the thing, mastering the code itself means absolutely nothing if you don't master the mark scheme rules. So, the crucial point is understanding why these rules exist, and is to ensure completely unambiguous technical understanding. Rule 1. 1 mark equals 1 distinct technical point. Please don't waste precious exam time repeating the same idea twice hoping for double credit. Rule 2. Always use scenario nouns. If we were leaping through temperatures instead of random numbers, you literally must say input temperature, linking your logic directly to the context. Rule 3. Command words dictate everything. State means you just need a quick factual point. But explain, that means you need to provide the mechanism and the why behind it. Know this exact blueprint and you can map out a flawless answer for any algorithmic challenge they throw at you.
Now, to make sure you never walk into a Cambridge exam unprepared again and to keep getting these direct mark scheme blueprints, you need the right tools in your feed. So subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. We are constantly breaking down these complex concepts into manageable, actionable steps so you can walk right into that exam hall with total, unwavering confidence. So, you successfully survived this flowchart loop. You know exactly how to build it, how to initialize it perfectly, and how to test its boundaries. Awesome. But what happens when the examiner suddenly swaps the command word from write an algorithm to evaluate this algorithm and throws a fatal, completely hidden logic error trap straight at you? You really need to know how to spot the invisible mistakes that everyone else misses before they completely destroy your exam paper. Seriously, don't let the examiner take your hard-earned grade back. Jump straight into our next explainer, focusing on common logic traps right now, and let's secure that top grade together. I'll see you there.